Today is July 11th, 2015, and this is the biggest, the most important idea that I think is completely glossed over by the chemists of the world and should have been one of the most obvious things that any chemist, geologist, or astronomer should have realized. Unfortunately, a lot of the groupthink has taken over. I'm going to explain this in as easy language as I can, so people who don't even understand chemistry or astronomy or geology can understand. So here we go. The sun's composition is comprised of these main elements. Okay, you have the sun shining, and we found out what it's comprised of. Obviously, it has hydrogen, helium, oxygen, carbon, iron, neon, nitrogen, silicon, magnesium, sulfur, and every single element that occurs naturally in there in amounts lower than 0.04%. So imagine the entire periodic table is all the way down, but these being the most abundant. When a star cools, okay, these ionized bits of matter, remember, when the star is in this plasmatic state, all these are ionized, meaning they're not connected to other elements. They're free-floating as a plasma. You have charged iron, charged neon, charged nitrogen, charged silicon, charged magnesium, charged hydrogen, a whole bunch of that. So what we can do here is understand something quite simply. If this thing cools down and all these elements lose their charge by combining with other elements, they produce what are called molecules. And we have evidence for these molecules all over the solar system, and are even standing on some of these molecules. Hydrogen sulfide, when you take hydrogen in its ionized state and combine it with sulfur, you create hydrogen sulfide, also known as sewer gas. This is what stars do. They make hydrogen sulfide. H plus C, hydrogen plus carbon. When you take lots of hydrogen and combine it with lots of carbon, you make hydrocarbons. Natural gas, oil, every single hydrocarbon that's ever naturally occurred is basically a result of a star's evolution. As it cools and dies, the hydrocarbons stay put. Iron hydride, iron and hydrogen. This becomes an alloy at 35,000 atmospheres of pressure, so it's a good candidate for the interiors of gas giants. Not metallic hydrogen. Metallic hydrogen is bogus. You have to add iron in there because there is a whole bunch of it that can make metallic hydrogen. NH4, ammonia. This is very, very common in evolved atmospheres. Look how much there is. Lots of nitrogen, lots of hydrogen. That's what happens. The nitrogen combines with the hydrogen in the stellar atmosphere as it cools and shrinks and dies, and the material recombines into chemical compounds. Here's a familiar one. What happens when you take a lot of hydrogen and you combine that with oxygen? Where's oxygen at? Oh yeah, look, the third most abundant. That's why water is abundant all over the place. Water is a direct result of a star combining hydrogen with oxygen, and which will rain down in its interior. And we even have leftover of this process. Well, not the actual combining hydrogen with the oxygen, that's already done via plasma recombination. But we have water to water vapor, and the ice. We have that cycle, the other three-phase transitions for it. As well, we can make nitric oxide inside the sun. We can make nitrous oxide inside the sun as it evolves and cools. We can even make silica, which is quartz, a main component of beach sand, a main component of granite, and gneiss, which are basic minerals, which I guess these would be considered rocks, and the mineral would be considered quartz. Of course, you mix mica, feldspar, and I think biotite in there as well. And then you have magnesium oxide, which is a lot of periclase, which is an oxide mineral, a different type of mineral. But the main point is here. Imagine every single molecule on the Earth being completely ionized to where there are no molecular bonds, but the actual element is there. So you completely break down this molecule and leave the elements alone, and to see how they would sort themselves. Which element would take up the highest position? Which one would have the most energy? And which one is was lightest, the lightest one? Hydrogen. Second, helium. Now helium and neon, they are what's called, noble gases, so they are supposedly reactive, but as we can see here, when they are ionized, they actually were very reactive. No, that's helium, my bad. Hydrogen is very reactive. So helium and neon are the two least reactive. This is why there's not many compounds made of those two elements. But I think we're finding compounds made of them currently, but more on that later. As long as you guys can get the main point of this, is that when a star is hot and plasmatic and shining, a lot of the material is ionized. But when it cools and shrinks, all those elements combine into molecules in its interior. And it cools and shrinks. And it cools and shrinks. And it cools and shrinks. Meaning that as the star is heated really hot and it cools down, these elements combine with each other, making molecules, and they stay put. And depending on their properties will determine where they end up on the interior of the star. So basically what we have here is not only a wide difference between new theory and old dogmatic fusion theory, but that we can completely replace it with actual science, with actual chemical reactions. And I highly doubt the chemists of the world are going to acknowledge this, because they don't consider plasma to be a phase transition, or a phase, in other words. So you have plasma up here, and you have your gases, and then you have your liquids, and the solids. And given how the actual reactions go, when the star is hot and young, it's right here, and then starts combining into gases, which are superheated, and supercritical gases, or supercritical matter, I should say. And that material then obviously condenses into liquids or solidifies into solids. And this would be called deposition, and this would be called, condensation, and this would be called recombination. And as the star loses heat, it goes down here. So the oldest stars will be comprised of liquid and solid of these molecules, and the youngest, hottest stars are mostly plasmatic, and the middle-aged ones are mostly gaseous and full of supercritical matter. Of course, there are a lot more chemical combinations that I haven't listed here, but to really understand that stars synthesize chemicals as they evolve is to be light years beyond modern science as it stands today. Hopefully we can get chemistry and geology and astronomy into one single interdisciplinary science, because that is what it is at its heart. They're not separate sciences.